at all? Maybe I can put the microphone there because it's also like it's both side and here probably with this room that I hate, but that's where we are, I suppose. So how about this? Voila. Prova. Ooh. Do you hear me better now? Let's try to do this thing. I think it's better now, right? Okay. So we start. Are there any questions about what we did last time? Or you're all okay? You have the slides from today already online, so I'm gonna try to upload them before the class every time. So, yes. So we take today is about two things. This week it was supposed to be about Hopfield networks, but before talking about Hopfield networks, Hopfield is the guy who won the Nobel Prize this year. So it's good that we study him, what he did somewhere. And so today's topic is actually like a continuation of what we did last time, because I'm gonna show an algorithm that shows how the weights in a perceptron are learned. So we show the algorithm and we prove that it converges. So it's good that sometimes algorithms find the solutions because that's what they're supposed to do. And second, we're gonna talk about bidirectional associative memories, this BAM thing, that is necessary to start talking about the Hopfield model. So from Friday on, we're gonna do Hopfield networks, but before we do this preliminary pre-Hopfield thing, okay? So kind of half of the lecture is gonna be perceptual learning, even a little bit more, and the rest is gonna be BAM. So to start, we need to do some stupid recap, but yes. We talk about Euclidean scalar product. Dot product, we've seen it everywhere, I suppose. If I have two vectors D and W belonging to Rn, then I define the scalar product between D and W as this. Okay. I just do the dot product, and this is also equal to the norm of B times the norm times the norm of W times the cosinus of the angle between the two vectors. Okay. So what do I mean now?
A bit larger.
Do people see? Yes. People don't see online?
No.
Well, it doesn't come to class. Yeah, I don't know. I'm gonna be write larger later. If I have a vector V, imagine that I have, sorry, the vector W is fixed. This is my vector W. We're interested in the sign of the scalar product for the algorithm. That's why I'm doing this recap. So if I have this vector W, and I imagine that I'm moving my vector V, the scalar product is positive whenever V is inside this, is zero whenever V is on this line, and is negative here. Not everyone agrees. Because it depends on the cosine of the angle between the two. So if I put my V here, it's gonna be less than 90 degrees. And if you're gonna put it here somewhere, it's gonna be more than 90 degrees. And if I put it here, the angle between V and W is 90 degrees. So the cosine is. So these are also always positive, let's say. So what determines the sign of this thing is the cosine of the angle between the two vectors. I'm not saying anything shocking today. Not yet. So this is one thing. So there's another thing I want to recap. That is this property, I suppose everyone knows about it. If I have two vectors V and W, sorry, if I have three vectors, zeta, V and W, and I want to do V plus W scalar zeta, then I can do it's B scalar zeta plus W scalar zeta. Nothing crazy, it's everything. So what I was talking about last time was the following. No, okay, this is where whatever I say here, you can find it in the book, just for this week as well, because also upfield networks are in chapter 13, as well as BAM, whereas the perceptron learning is in chapter 4, section 4.2 for the convergence of the algorithm. I'm just gonna, I mean, if you feel lost or if you don't like the way I speak, the book tells the same things, but in a written way, whereas I talk. Perceptron learning. So we were talking about perceptron computable functions. And we were saying that a perceptron can compute a function that goes from R something, Rn to 0, 1. If there is a way that to find a hyperplane or a line, for example, if it's R2, that divides the preimage of 0 from the preimage of 1. So if I find a line that separates those two, then I can find a perceptron because the line determines all the parameters in the perceptron. So finding a line is equivalent to finding a perceptron. This was last time's story. And I remind you that this was the condition that the line was the line of the hyperplane in dimension n at this equation. But I was also talking about biases. So you could like bring this here and do this. So put the thresholds to theta. Sorry, with the threshold theta to 0. The activation function was the Heaviside step function like this on the nodes. But if you put theta to 0, this is just the sine function. When theta is equal to 0, this is the sine of the x. The sine function is equal to 1 if the thing is positive or equal to 0, and it's 0. Okay. Have you ever seen this? Yes? No? We don't care. We call it the sine function, like minus and plus. It's the Heaviside step function with theta equal to 0. So why it's easier to check for signs on the nodes instead of checking for thresholds. And what we did was, did I put this here? Click on the video. Where is my mouse even? Yes. Okay. Yep, not what I wanted to talk about. Okay. So last time we saw that we could bring this on the other side and treat the threshold as a weight. So we could adjust the thresholds together with the weights because we want to be able to adjust the thresholds. So we were considering this was in the input space, a line in the input space or a hyperplane in the input space. But in this case, we were considering the extended input space. So we were adding one, maybe I can show you the picture so it's easier. This yes, this previous one. You remember this picture? So we were considering like v w n plus 1 equal to minus theta and x n plus 1 equal to 1. So all our input had an extra coordinates called x n plus 1 equal to 1. And the weights were, the new weights were with the threshold. Plus 1 copy I and 0. Okay, this was the thing. But now, since I did this fabulous recap, then I can just say that this is the scalar product of the weights vector extended and the nodes vector extended, so with the 1. Means that all my x's are like this, x1, xn, 1. For people who do mathematics in the past, this is somehow related to the projective space and choosing an affine space in a projective space at a bigger dimension. But if you don't care about projective space, it's fine. But yeah, so this is the thing, and this is related to the scalar product, okay? We come back. So what did we do last time? We saw the XOR problem. So the fact that the XOR function was not perceptron computable because we were not able to find this line that separates the value in which the function takes is 0 from the values in which takes value 1. So XOR minus 1 of 0 is not, I cannot find a line, and we prove that this line does not exist, okay? So the property that we need to generalize that the XOR does not satisfy is this so-called linear separability of two sets. And those two sets are the pre-images of 0 and 1. So we showed already last time what is this definition. So if I have two sets A and B in an n-dimensional space, we call that, so the unextended space, we call them linearly separable if you have n plus 1 real numbers, so n plus 1 weights, where Wn plus 1 is minus theta, such that every point in A satisfies the equality greater or equal, and every point in B satisfies the equality with the strict tree. In other words, this thing can be said in this way. So for every point in A, we have that x scalar W is greater or equal than is extended though, because we put 1 it's greater or equal than 0, and that for every x B, x times W smaller. This is the same thing, okay? So roughly speaking, I can find a hyperplane because this thing is a hyperplane that separates the points in A from the points in B in the extended input space. And in this case, the hyperplane can touch the points in A because the equal is in the points belonging to A. So again, a remark, we said this last time, but if I satisfy this condition, so if my function has the pre-images of 0 and 1 that are linearly separable, so if this line exists, then I can write a perceptron because this line gives me my perceptron. So a perceptron computable function is like defined by this line somehow. Okay. So we defined also this other thing that was absolute linear separability. So essentially it's the same thing, but strictly greater here. So when you have absolute linear separability, the hyperplane doesn't touch any point of A and B. Before it could touch, like the point of A could belong to the hyperplane, but in this case, we have strict inequality for both of them. So the same thing. Okay, why are we defining this? Because in the end, I mean, if you have the points of A and B that are finite sets, so if A and B are finite, we don't really care about the difference between absolute linear separability and linear separability. Because if there is a finite set of points of A and B, imagine that this is my domain. I don't know, my domain is R2. My function goes from R2 to 0, 1. Okay? Imagine this, we have this, and we have a finite set of points. I call dots the ones that are sent to 1, and I call cross the ones that are sent to 0. If I can find a line that touches some of those and that separates, for example, this touches this point. Since the set of points is finite, I can always find another line that doesn't touch this. I just move it a little bit. There is a proof for this, but the proof is like essentially based on the idea that if I have a finite set of points and a line that touches one of them, then I can move it. I'm not gonna do the proof, but it's on the Rojas if you're interested. So, what is going on? Now, the perceptron learning algorithm is about having two sets, okay? And we want to find a vector W such that the hyperplane orthogonal to this vector, okay, let's come back again. Let's come back to this, okay? This is an equation of a hyperplane. The vectors W, so the coefficients W are the normal vector to the plane. So it's a vector that is normal to the other plane. So we want to find a vector W such that the hyperplane associated to this vector W absolutely separates the sets of P and N. We call him P and N because P is the positive with respect to W and N is the negative with respect to W. So it's like we're looking for, in this example, I was fixing W and I was telling you, oh, what happens when I move the other vectors. But actually, in this case, the points are fixed, the points that we know that should be positive and should be negative. And we know that they are separable because we assume that. We assume that the function that we want to approximate has this property of like being able to put something in between the points that should be positive from the points that should be negative. So if we assume that, now like the question is more about finding the vector, and the points P and N are fixed. So we want W such that all the points of P belong to the open positive half space, and all the points in N belong to the negative half space. So now we assume that P and N are in the not extended case. So we have the threshold, right? We are in dimension N. So we assume that right. So we have P and N are two sets of n-dimensional vectors. So they are both subsets of Rn. Okay. And what we want to find is a vector W that belongs to this one now. Yeah. We want to find W that belongs Rn such that for all x belonging to P, x times W is greater than 0. And for all x belonging to negative, yes. So we are looking for the absolutely separable. So without this, x times W is less than 0. Okay. So this is the algorithm. What does it do? We start from a random vector of weights, W0. Chosen randomly. There is also an heuristic way of finding a certain W0 such that it works. It goes a little bit faster, but we'll see that later. So we choose a vector and we set the time equal to 0 at the beginning. So we agree that whenever we have a point that belongs to, so we check on the vector. So what it does is in the test phase, it picks a vector belonging to P united N, and it checks if it belongs to P and this is true, it is classified correctly. It starts using like some learning terms at this point, the book. Like this is like the training set. So like we have these things that are supposed to be positive and the negative. And I'm looking for the function that tells me that tells me is able to classify the positive and the negative. Okay. So if I pick up an element in P or in N such that this is satisfied, because in the test phase in this line, a vector x is selected randomly. If this is true, then it is correctly classified. So I come back to test again. Okay. The vectors that satisfy that belong to P and do this, belong to N and do that, are correctly satisfied. Are correctly classified. So I move on. The question comes, well, what if I find in my random selection process something that is not correctly classified? So what if I find a vector? So if there is two cases, if it exists an element in P such that W times, so W0, W at the time t, so at W is updated just if we find something like that. So imagine that way I'm at step t, so WT times X is probably classified, so something that's supposed to be positive is classified as negative or equal to 0, or in the other case, if it exists an element belonging to the negative, it is wrongly classified. So what it does when I'm in this first case is that I want to bring, so this is negative, I want it to be positive, what I do is make it bigger. So I update, in this case, I update W. So it does this thing, add the thing. Yes. I update W, and instead of WT, I obtain WT plus 1, which is equal to W plus X. Whereas when I'm classifying wrongly some negative guy, what I do is this, the contrary. WT minus X. So what I mean is that my scalar product was negative. I want it to be positive, so let me show that I'm actually doing this operation, I'm actually increasing it or decreasing in this case. Let's consider this case. So if I do the scalar product of that number, t plus 1 times X, what I obtain, since I showed you the property before, is that WT plus X times X. So that WT times X plus square the norm of X. And this is positive. So I have something before, but I'm increasing it, so like I'm trying to make it positive. Like this is negative, I want it to be positive. So this operation makes the job. That's what I want to do. Okay. And analogously for the other case, in this case, WT plus 1 times X is equal to what? WT minus X times X. So it's WT times X minus the norm of X. This thing was positive, I want to reduce it, so I subtract a positive one. I hope greater than 0, that's why I have greater than 1. Okay. There's other ways of like, okay, in this pseudocode, by the way, there is, so it does that, it adds and subtracts and then comes back. There is no step in this pseudocode that tells you, okay, when all the vectors that I have is fine, so where everything is classified correctly, just stop. It doesn't stop this. So, but this is the idea. Okay, this was what I was saying before. So yeah, I'm checking the sign of things. So it's clearly that I'm not having biases. Here I wrote belonging to Rn, but actually I'm working in the extended input space. I want to make it like a tiny parenthesis about what the hell is the difference between extended and the not extended input space by doing a drawing. I don't know if it's useful, this geometric intuition or not. It's not super important, I suppose, but yeah. Yeah, now maybe another thing that might be useful, like, so when you have X, imagine that you have X and W that are, in this case, okay? In this case, when a positive is wrongly classified, what is going on? Like imagine that X is X. It's supposed to be positive. But the scalar product with WT at step T, this is WT, is negative, right? Because this is the line that determines the sign of WT. This is X that is supposed to be positive, but WT classifies it as negative because all these things are positive and all these things are negative. Okay. All these things are negative for the scalar product with respect to WT. So when I add to WTX, what am I doing is that I'm actually moving X, moving W a little bit closer to X. So the same thing like I showed from the fact that the scalar product is either increased or decreased, can be shown geometrically by doing the sums of the vectors. So I do the sum. This is WT plus 1. Okay? And you can see that in this case, with respect to WT plus 1, so X is in the positive part because this is WT plus 1 and X is now in the positive part. So this operation of bringing WT to WT plus 1 classifies correctly X in this case, goes in the right direction. And one can do the same thing for the second case. So imagine that I have, this is X here, and this is WT. So the scalar product between these two is positive because X belongs to, this is orthogonal to the upper part with respect to WT, but I wanted X to be negative. This is like negative, but I wanted it to be, sorry, but I'm classifying it as positive. So I have to move WT. This is like the subtraction operation here. So what is going on is that I do the difference. So I do WT plus the opposite of X. This is minus X. Okay. This, I'm sorry, yes. This is WT plus 1. And now what is going on is that X, this is not really better, but a little bit better. This is the orthogonal with respect to WT plus 1. X is in the negative side. And it's a bit confusing, but what I want to say is that it's the same thing, but using the vectors. Okay? Yes. Now I wanted to show what's the difference between doing everything in the input space, these operations in the input space, or in the extended input space. Let's show the case for R2. Okay. Input space. Extended input space, extended. It's clear that since I'm checking signs and not thresholds, all this crap is going on in the extended input space. But this is equivalent to the input space. It's just like harder to draw. So input space is R. When I do extended input space, I'm kind of in R3. Imagine it's like my problem is this. I have X1 and X2. And I have my many points, all my points that I call the positives and all my points that I call the negative that I'm trying to separate. I'm assuming they are linearly separable. So they're not like the XOR problem. Those are actually, it exists a line that splits them. I know that as a hypothesis, so I don't care. But imagine that this is my input space. When I look for a line, I look for a line that can be anywhere, is not forced to pass through the origin. And the equation of this straight line is W1x1 plus W2x2 equal to theta. This is my line, okay? And in both cases, actually, the weight vector, imagine that I found a vector that separates, like my vector star or something, my favorite vector, whatever, that has these coordinates, W2 and minus theta. Okay? Imagine this is the solution, like what the algorithm finds, okay? What happens in the extended input space? Because this is where I'm computing, actually. Okay. This is where I'm doing because I'm checking for signs here, just positive or negative, okay? So Since when I go to the extended input space, I take a vector x1, x2, and I send it to x1, x2, 1. All this thing, all this plane is mapped to this is x1, x2, and I'm calling this x3 to be good. And so I'm sending all this plane into the plane of equation x3 equal to 1. This is a plane, because you have just one equation in a space of dimension n, you get something of dimension n minus 1. So essentially the plane is sent to, if this is height 1, my plane with all my points, etc., like all my problem is sent to this plane at height 1. And what is the line? What is this line? Because this line was not forced to pass through the origin, because it had this coefficient theta. This line is just another plane. So is another plane of equation. Like what I'm moving here, actually, because I'm moving, sorry, I think I did it badly, because like the points were actually with like x and 1 added at the end, and the weights were actually the weights and w1, wn plus 1. So, but yeah, when I'm looking for this line and I'm adjusting my weights, and my weights are like all these three actually, like I'm moving all the three. I'm actually moving a plane that passes through the origin, and it's the plane of equation w1, x1 plus w2, x2 plus w3 that is equal to minus theta, x3 equal to 0. Okay? This is a plane because it's still one equation in dimension 3. And my line, in this case, is just the intersection of two planes. So if I do the intersection of two planes, I'll take a line. All this just to say what is happening geometrically when I pass from the input space to the extended input. Let's move on. Yeah, so this is a better picture if you want to see on the slides. What the hell? Yes. This is the same thing. And he put P and N for negative and positive. Yeah. I hope it's fine. Yes. This is just what I just said. So essentially when a vector that is wrongly classified and was supposed to be positive is moved in a way that is more to the positive side with respect to the new vector. So it means that the angle between him and the weight vector that is wrong is greater than 90 degrees, whereas it's smaller than 90 degrees when I'm in the case of a negative vector that was wrongly classified as positive. So it's too close to x, w, so I have to move w in order to have x classified correctly. Yeah, okay. This algorithm does not stop. Yeah. Yeah. Also this, whenever we update the weights, we're doing some kind of rotations because as I said, like we move the weight vector. For example, in this case, we were moving the weight vector from here to here, and here we were moving the vector from here to here. Okay? But the rotations are not all even because when I'm adding x, or the transformation that is applied to w is to add x. X is fixed. So whenever I fix a point, I'm adding a vector, okay? But since the vector has not norm 1, or the rotations that I'm applying are not going to be the same. If I add x many times, imagine that I pick a vector x that is wrongly classified, and then I change my w from wt to wt plus 1. But wt plus 1 was not classified yet x. So before I was adding wt plus x. Imagine that wt plus 1 does not classify yet x. So I do again plus x. So since x is not a vector norm 1, the rotations will be different. Like we will change because none of the vectors that we're using is normalized. Yeah, I didn't recap what normalized means, but means of norm 1. So I take a vector and I divide it by its root. But yeah, let's move on. Is it time to take a break? Okay. This is an example of how these things work. And actually, we're considering an example in which all the points are positive. So there is no negative points. I have x1, x2, x3, x4. I don't know if you can see. It's pretty bad. But yeah, imagine that you're starting from your first vector is w0, and you can see that x3 and x2 are the green side is the negative. So x2 and x3 are correctly classified, but x1 no, because it's supposed to be positive. So what I do is to sum w0 and x1, I obtain w1. So I'm in the second case. And now I see that something that was before correctly classified, now it's not correctly classified anymore. If you see x3 in the second step is not correctly classified. So what I do is to, again, my algorithm picks randomly x1, x2, and it says everything is fine. But when it picks x3, it says it's not fine. So it does the sum between w1 and x3, and you obtain w2. And then you see that now x1 is again not correctly classified with respect to this new weight vector w2 at the step 3. So what it does is to, again, try to correctly classify x1. So it does w2 plus x1. And so you see that there's many things happening. The norm of w is increasing. The more you started with a small w0 and then it's increasing. And also the adjustments are the more you advance, the more the adjustment becomes smaller and smaller. So there is names in the literature for these things. Like, so each correction rotates w for a smaller angle. So that the first corrections are more brutal and the last one are more smaller. So yeah, the learning rate, so the way w changes becomes smaller. And so if I already did many steps, one of the latest steps would do just a little correction to put the wrong vectors in the right zone, let's say. And so there is this concept that in this case, like in this algorithm, is kind of like not explicit, but it's something that you see happening when you compute it on the vectors, is that there is some kind of learning constant that goes to 0, and is the rate of like change of the vector w. So the more you learn, the more this constant is going to 0. And it talks about degree of adaptivity or plasticity of the network somehow. Like the w is like corrected less and less the more you train the network. So. But yeah, maybe I'm gonna do a break now because the next step is to show that this algorithm converges. So maybe it's better to do a break now. Yeah. Or 5 minutes if that's okay for you.
Sharing really quickly the slides because they weren't shared.
They weren't shared?
I was showing the stuff that you were writing there.
Yeah. So the proposition we want to prove is that a good vector W star is found in a finite number of steps. So that's geometrical visualization because you have to imagine that your positive and negative point, your candidate positive and negative points that are supposed to be linearly separable, absolutely linearly separable. Same thing because you have a finite number of P and N, positive and negative. Imagine that in a plane. Then you put this plane in 3D, so this plane is like at height 1. And then what you're doing, your algorithm is doing is taking a plane determined by the parameters of the vector w, and you're moving the plane until the line in which this plane intersects your plane with your points separates those points, the positives from the negative. This is what is happening. So P and N are finite, so absolutely linearly separable is the same thing as linearly separable. So what we want to prove is that the algorithm that I showed you before updates the weight vector WT a finite number of times. So let's go. Now, before this, there is one thing that you can try if you want. Try to draw like a set of what is the choice, a good choice for W0. So imagine to write a set of P and a set of negatives somewhere, I don't know, here, okay? And he says that if I take those are my PIs, P1, 2, 3, and my negative ones and 1 and 2 and 3, instead of X, I say P and F, positive and negative. But he says that a good choice for W0 is actually the average from I that goes from 1 to K, PI, minus the average of I that goes from 1 to H and I. And so, what am I saying? I do the average of the positive ones, I do the average of the negative ones, I do the difference, and that would be hopefully close to a good W0 to start, and not to start completely random. You can try to do it with arbitrary numbers and see that it's kind of close to a straight line and separates. Yes, this is just a heuristic consideration. It's not proven, but yeah, do that works kind of okay. So let's prove this result. First, we are gonna do 3 assumptions that do not reduce the results. So 1, 2, 3. The first one is instead of using positive and negative, I'm gonna use positive y. That is the positive united to the negated negatives. Why am I doing that? Because for the positive, what I check is this, right? Whatever WT I have at whatever W I have at step 3, I check if it's positive, okay? But and for the negative, for the x, I do this for the, that's what I want. For the x that false. For the x's that belong to P, that's what I do. And for the x's that belong to N, what I want is this. Okay? But what is the negated N? I define the set of negated N. That's crazy, but it's like the set of all the x's that are minus x such that x belongs to N. Okay? So whenever I test the negativity for an element in N, it is equivalent to testing the positivity on an element belonging to minus N. Because this is true if x belongs to N. This property is true if and only if I don't know, minus x times WT is minus 0. Yes, let's do that. This property is equivalent to saying that W times x is greater than 0 for all x belongs to N. So if the x is belonging to N satisfy this property, the x is belonging to minus N should satisfy the opposite because they have just a negation. And when you put a minus, you change also the sign of the inequality, that's why. These are equivalent. So instead of testing positivity and negativity, I just test positivity of P and N minus. I don't care if some elements of P belongs also to N minus, I will just have a double, like I will have less points. Is that okay? Second thing is that, oh God, instead of considering the points of P, like I take all the vectors in P prime, sorry. And instead of taking as they are, I normalize them. So whenever I have x that belongs to P prime, I consider instead x divided by the norm of x. Instead of taking random vectors as positives and negatives, positive in this case, all of them are positive. All my negatives, like I switch them to the positive side. I take them as having norm 1. Why do I do that? Why can I do that? Because whenever I check for positivity, I don't care about the norm. Whenever I check, the thing my algorithm will check is this, is whether whether x times WT and step t is greater than 0, that's what it's asking. But what if I put like a positive constant? If I take a constant k, positive constant, and I multiply by it, it's the same. The sign does not change. Okay? So in this case, k would be the norm of x, 1 over the norm of x. I don't care whether the vectors that I'm testing for have norm 1 or not, but since the computations are easier when they have norm 1, and this is equivalent, I will just don't care about the norms of that points. And the third condition to check for is that I'm assuming that a solution to this problem exists because my two sets, P and N, are absolutely linearly separable. So a line exists. So like one good vector that does the job exists. Let us call it W bar. It exists by hypothesis. So instead of taking W bar, I take W star. That means W bar divided by C. So essentially what I'm doing is that I take also this with norm 1. It exists, so I can do that. And it's not the zero vector W. Because I recall you that on my R3, there is my plane here and I'm intersecting with another plane. Is not 0, because otherwise it will be like, there will be no plane. If I take W as all zeros, there is no plane. Because my plane has the equation W1, X1, for example, in R3, W2, X2, plus W3, X3. Those guys cannot be all 0, otherwise I don't have a plane. So this norm is different than 0. And this thing exists. Okay. So just to recap, I'm taking all positives because I'm splitting the negative towards the positive. I'm taking all the points that are positive, that want to be positive, like, as having norm 1. And I'm taking also my goal result that I call W star as having norm 1. Okay? And those are my 3 hypotheses with which I work. Now, consider, like, to start the actual proof, this is like extra hypotheses that do not reduce the result, okay? Consider that imagine that I am step t plus 1. Okay, I'm gonna put you the steps also on the slides, so don't kill me. I go there, okay, instead of using axes everywhere, now that I said that everything is positive, I go over 1, N, belonging to P prime. Those are my points, okay? Imagine that I'm at step t plus 1 of the algorithm, okay? Like I computed the step t, and now I'm step t plus 1. So I have a weight that I call weight t plus 1. I'm asking myself how this weight wt plus 1 is far from my w star that I want to reach, right? Because I want to prove convergence, so I want you to see whether, like, with t that goes to plus infinity, my w where I am now is far from my aimed w. Like, do I even reach it? Like, is the time when I reach it finite? That's the thing. Okay, this is wt plus 1 that I calculated at step t plus 1. Since I calculated it, it means that at step t, I was wrong at classifying something, so I had to update my w, right? So this wt plus 1 comes from wt plus some pi. Because I update with plus, because I only have pluses, I don't have pluses and minuses, okay? So I'm just doing the add operation in the pseudocode that I have, okay? So WT plus 1 is equal to WT plus PI, because WT was failing at classifying PI. Since I am at step T plus 1, I did something wrong in the previous case. Otherwise, I wouldn't have updated my weight vector, okay? So this means that WT scalar PI was misclassified, so it was smaller or equal than 0. Because when I want to classify, I want all the, my goal is to have my W star scalar PI greater than 0 for all R. Right. This is what I want to reach. This is what happened in the previous step. Okay. Now, I could draw the angle between T plus 1 and I call this angle. And when I show convergence, what I want to show is that the cosine of rho somehow goes to 1. So the two vectors are getting closer in finite time. Let's show this. We have to calculate this and use all these. The cosine of rho is equal to, okay, when I talked to you about scalar product, I was saying that the scalar product between two vectors V and W is the norm of one times the norm of the other times the cosine of the other between the two. So I'm just gonna use this formula here. So it's like W star times WT plus 1 divided by just the norm of WT plus 1. Can someone tell me why I'm not dividing by something else? Why am I just doing this? Shouldn't it be here another norm? No? Shouldn't it be here the norm of W star? Why am I not going to do this? I'm investing in this formula called the cosine. The scalar product is related to the cosine, right? But here I have two norms, the norms of the two vectors. Why am I not putting this here?
Nicoletta, your microphone fell.
Yeah?
Over there. Look. No. The
No, I think it isn't that. It just turned off.
Nicoletta.
Oh, here. So someone knows why I'm not putting this norm. Like anybody, please. Yes. Because we are assuming by hypothesis that W star has norm 1. W star exists, so I want to reach a vector of norm 1. I don't care. We know it exists. So it has norm 1. Yes. So this is what is going on, right? Okay. Now, we consider this and this separately. Because what I want to do is to put some kind of minor, equal, or something that I don't know. Okay, this is my goal. I go 1 with the operation that concerns the numerator and 2 with the operation that concerns the denominator. So don't go crazy. 1, what is going on? I take this W star times WT plus 1. What is going on? What's the definition of WT plus 1? I take it from the other black hole at home. W star times what WT plus PI. Right? I just took the definition, I don't know. The definition, this was after you did from this one and this, because the algorithm was wrong at step 3 on the point PI. It exists a point PI such that this is true. What is going on? Now I just multiply W star times WT plus W star times PI. I just told you that the algorithm was wrong on PI. So this means that this thing was actually equal to 0. Because PI is supposed to be positive, but the algorithm was misclassifying it as negative. So what does it mean? Oh God, no, this is wrong. No, WT on PI was doing that. What is it doing W star on PI? It's classifying it correctly because W star is like the solution we aim, like the final solution. So this actually is good. It's classifying this correctly, so it's greater than 0, okay? It's strictly greater than 0. So that's why we need like absolute linearly separable, linearly separable, because I'm using it now. It's not equal, it's greater than 0. So what does it mean? That PI is greater than 0 means there exists a positive constant delta I. This is detached from 0, so I can pick a number in between. I put I greater than 0 such that I star times PI is greater than delta E is greater than 0. I can pick a number in between. A positive number, okay? As a one. This is a positive quantity, strictly positive, so I pick a number between 8 and 0. Now, let's put it equal here. It's equal to a positive constant that is greater than 0, okay? Now what do I do? And this is for PI. But W star is correctly classifying all the P's for all the I's, sorry. So for every PI, there is a constant delta I such that this, okay? So I got delta, the smallest one. I take all the points, I do this, and I take the smallest constant among all those constants. One, this. That is more, I don't know. I don't want to. W star times P for all P that belongs to P prime is the same thing, just written. Okay, that's why we need absolute linear separation. So, why do I need this? Because I can say that this is greater or equal. So this in particular is greater than the minimum constant. It's equal to its own constant, but if I find a smaller constant with another point, that constant will be smaller than that delta. So W star times WT plus delta. And this is where we are. So keep in mind this is 0.1 because we're doing 0.2 now. Cancel it. I know we're doing 0.2, we need to do our own stuff. Now, I did this for step T. I do induction, so I do for all this. For example, I did this. WT was calculated, so at the step T minus 1, the algorithm was misclassifying some point, Pj. So, meaning that this part is greater or equal than W star times WT minus 1 plus delta. Just this part. I do the same thing I did for this. step is for the previous step. Okay. So what I obtain is that this scalar product plus delta. The algorithm step, since WT was calculated, was misclassifying something at the step t minus 1. So I have to do this thing all over again. And the delta sum. So if I do this again, I will have another delta. So what does that mean? Induction over Q. I will do this. I can arrive until W0, basically, the first W I have. All the steps I did, I come back. Okay. And the delta sum. And this stays the same. So W0 plus T plus 1. You can see that this is T and you have just one delta. So it's T plus 1 delta. This is T minus 1 delta, 2 delta. So that's the number of times you sum delta plus the index of the W should give you T minus T plus 1. So this is 0 and T plus 1. This is T minus 1 and 2 delta. This is T and just 1 delta. Yeah. So, this is what happens to the numerator. In the end, what we obtained is that this thing is greater or equal than W star times W0 plus T plus 1 delta, where delta is a positive constant. Let's look at the denominator now. That is supposed to be easier because it's just one term. Okay. W plus 1. Oh. Yes. So it's just the norm, but I'm gonna do this because the computation sets are easier. And then I'm gonna take the square root and take it away. That is WT plus 1, scalar product WT plus 1. What does it mean? And I'm doing WT plus PI scalar product WT plus PI. And I do all the multiplications. The scalar product is commutative, so it's gonna be fine. So what I obtain is that the squared normal WT plus 2 times WT scalar product PI plus the squared normal PI. Can someone tell me something about this as before? This is equal to what? Because one of the hypotheses, all the P, I take all the points as being positive because I just switch the negative on the others. So this norm is equal to 1 because I assumed it. What is going on with the rest of the sum? This thing, WT was misclassifying PI. It's not W star this time, it's WT. Right. It's misclassifying PI, meaning that it's supposed to be positive, but it's like negative or equal to 0, because at step t, I passed to step t plus 1, so it means there was something wrong at step t. So it was misclassifying. Yeah. So what is going on? Then what I obtain is that the norm of WT squared. So I can put this. Plus. Smaller or equal because it is smaller or equal than 0. And now what do? The same thing I did for step 1, sorry, this is step 2. Okay. What do I do the same thing? So I go by induction again. At step t, then the square I go to step t minus 1. Something was misclassified if the step t minus 1 existed. So what I do, I do less or equal, not less or equal, then what? Not down 0 square. This guy I didn't assume it was equal to 0, to 1, sorry, so it's left like that, plus 3 plus 4. Okay. So we want to put together, I'll do it right now, I need. So let me write here. So what did I learn from my step 1 and step 2 that I really use here? Because my goal is to show that, okay, what is my goal? To show that the angle of when I am step t plus 1 and my goal goes to 0, the angle, so the cosine goes to 1. Yeah. But the cosine is always, oh God, what did I do? I don't want to do that. No. I want to do this. Because I know that this is, the cosine is always more than 1. I want to do this. So if I find here something that explodes, it means that it grows for t that goes to here, for t that goes to plus infinity. So the more steps I do, okay, if I have some quantity that goes to plus infinity, it means that at some point the t's will be giving me the same thing. So that actually the algorithm stops at the minus 1. Okay, that's the goal. So if I have something that goes to infinity, it means that I stop at some point. So the solution was found. Okay. What do I put here? Why did I do all this? So result from 1 was giving me this, right? Greater or equal. Was giving me this W star times W0 plus delta times t plus 1. And step 2 was giving me this, that W t plus 1 squared was less or equal than W0 plus t plus 1. Actually, like if I do this, and I do the inverse. So like, because this is at the denominator. So yeah, don't let me rewrite it, but if I do this and I change the sign here. That's 1 over this. So this one is giving the equation. So with 1 in the numerator and 2 in the denominator. What I think is W star times W0 plus delta times t plus 1. And here I would take square root of W0 squared plus t plus 1. What happens when t, where this does this thing go, when t goes doesn't? So remember that this is a constant. I chose it at the beginning. W0 is my starting random vector is a constant. This is a constant as well, whatever. And the problem happens when I move t. I even told you that this is greater than it wasn't greater than 0 without some problems because Okay. I don't know if you like reading this, but all this thing behaves as if not like square root of t. Because if the numerator behaves like t, and the denominator behaves like square root of t. It's a t plus 1 over a square root. So for t that goes to infinity, that this behaves like square root of t. And it does that because the constant multiplying t is positive. Otherwise, it will go to minus infinity. Like this, when t goes to plus infinity, goes to plus infinity because I have a delta. So what is going on? This thing is exploding. What does it mean? It's not exploding. The more I restate t, it means that there is some t in which I don't do any more iteration. So the answer is correct. Okay. This was pretty bad, I don't know. And that's the conclusion of the proof. So yeah, you can have a look at like the steps that I put in the slides because like it's like all the details are there or in the top and you have the video and feel free to ask me questions. Yeah, so let me change topic. I think it's cool to say that we have an algorithm that actually converges, so it does the job. It's not just like random things. It actually finds the solution in a finite time. So that's the goal. Because what would we do with algorithms that don't work? Like we need them to work, otherwise what's the point? But yeah. So this is the thing. You can go in these slides, there's more details. So yes. I'm gonna do some how much time do I have?
15 minutes.
So we're gonna talk about something else that is needed to talk about hybrid networks. So I don't know. It's a good topic, I think, because the guy got the Nobel Prize this year. So it's good to study what he did. So first of all, this is the guy who got the Nobel Prize this year, and he got it with Geoffrey Hinton, and he got the Nobel Prize for physics. This got the physicists pretty mad because this is like one of the fathers of machine learning. So why, if someone coming from outside wins our Nobel Prize? That's the idea. But yeah, so what did he do and why did he got the Nobel Prize from physics? Probably the reply to this question is gonna come Friday. Because today I'm not gonna talk about what he did, but some kind of preliminary things. So first of all, the networks we've seen so far, so the perceptron and the mechanical units, and you've seen something else also in the first week, compute like there is an order kind of. You start from the beginning and you apply the weights and like then you change the nodes, etc. So things go in a certain direction. Whereas in upfield models, it's more like why this is inspired from physics, why this has any relations to physics, is that any computing unit is like a biological organism. So there is no synchronization. It's not that I know what the other is doing. I do what I want, and the other particles do what they want. And I see how the machines that work in this way interact. So that's why people say that there is no synchronization in this model. They don't update their nodes at the same time. Everyone does whenever he wants, does some update. So that's why also this model is inspired by particles. So you have to imagine it as a graph, like on the plane, with many nodes. And each of them is more or less connected to the people next to you, for example, the social network or whatever. You are more or less connected to some people in your life that are close to you or far, I don't know. And the weight tells you how much you're connected. So whatever you do interacts with the people you're connected to. But there is no synchronization. It's not like there is no global synchronization in some sense. There is no one that tells you, oh, now we have to everyone does the thing. There is no such a thing with networks. And so it is a model of, we say, unsupervised learning, because this thing you can prove that under certain assumptions, etc., converges to a stable state. So whatever it happens in this like chaotic definition, it's not chaotic. I'm going to define how the network computes, but what happens is that the network converges to a stable state. And you're not using a loss function. You're not using a function that tells you, oh, you're close, you're far. There is no such a thing. But so that's why it's unsupervised. There is no function that tells you, it's telling you whether you're doing good or bad. But the network, from the way it's defined, it converges anyway to stable states. So, and the reason is coming from physics somehow, because there is a function that is minimized, and it will be minimized anyways, even though it's not explicitly utilized in the network computations. That is the energy function. So this network computes and minimizes the energy. That's why it converges to a stable state. But it's unsupervised because the energy is not explicitly used in the computations. All these things very vague, but next time I'm going to say the equation, etc. So it's going to be more precise. But this is the idea of these models that are like drastically different from what we've seen so far. Okay. Unsupervised, I said everything, more or less. Let's go there. So why we have to, I'm going to talk about something that now is not like Hopfield networks. So Hopfield networks are asynchronous, so everyone does everything at his own time. So this model is useful for Hopfield networks for two reasons. The first one is that there will be an energy function in bidirectional associative memories. So these models are called BAM, bidirectional associative memory. And in this model, you have an energy function as well. And you have also the convergence to a stable state. So there are two features that are in common with Hopfield models. So they're kind of like something to transition from what we did before to what we're going to do next time. So what is a bidirectional associative model? So we have two layers. I'm going to show you a picture like this. And the arrows, okay, it's not written, but the arrows need to be drawn like with 2 points, like double arrows. Okay. What does this network do? You have 2 layers. You're not like many layers stacked in this case. You just have 2 layers of different dimensions. So you go, I don't know, n to the dimension of the first one and k to the dimension of the second one. The edges are bidirectional, means that you can start from this, we call it like forward step, the one that goes from the first layer to the second one. And then what you do is to come back through the same weights and through the same arrows. That's why the arrows have double edges. Okay. So what this BAM does is to go from one side to the other. That's how it computes. You start with an input, it goes on an output on the other side, and then the same output is put back, etc. So the activation function is like simpler than last time, so it's just a sine function. So heaviside step function with theta equal to 0. And yeah, the same edges are using to transmit back and forth. Let's write it properly. Do I write an example of dimension smaller? Yes. Do I have time to do that? That's what I'm going to do here. So let me do an example. This is the first layer, x1, x2, x3. The second layer is y1, y2. These are my notes. And I connect everything with double edges layer. This goes from 1 to 1, so I call it W11. This goes from 2 to 1, so I call it W21. W32, W31, what else? W2. Okay. So it's not very different from what we did. Why does this have 3 now? Yes. W1, 2, 1. Okay. I call the weight matrix in this case W. And I put the weights in this way. Well, W11, W12, W21, W2, W3, 1, W3. Yes, 2, 1, and this is 1, 2. Yes. Yes. So, I mean, the y's are obtained in the same way as we were doing before. It's not something completely different. So y1 is obtained by the sign, the activation function of x1 w11, because that's what comes from x1, and x2 w21. This is what's coming from x2, and x3 w31. This is what's coming from x3. And for y2, I do the same. So let me do it. So you can do matrix multiplications. Like this is what we did last time, just for each node, okay? You take the weights and what comes from those weights. But you do it for everything. So when you have like many, at the same time, you just put everything in a matrix and you apply the matrix. And it's the weight matrix. I think you've seen this in the first class. But yeah, so what it becomes is that the vectors are lines. So y1 and y2 is the sign of x, the vector x, that is this, w. So you start with the first vector x0, that is an n vector, and you do y0 times w on this side. And when you want to come back, you put the matrix in a way that you can do the multiplication to obtain something. So when you want to come back, you start with this x0, and you obtain a y0. Then you take this y0, and with the same weight, you obtain an x1, etc. x1, again, y1. And so on. So we call it like an iteration, a set of two of these, and a step forward and a feedback step. There's two steps for each iteration. So, yep. What's the question? So after m iterations, you have m plus 1 pairs of vectors, y's and x's, such that the y is obtained from the x with the same index, whereas the x is obtained from the y of the previous index. And so the question is, do I, at some point, wherever I start, I end up jumping between the same two states? So does this iteration lead to a fixed point? Where by a fixed point, I mean a couple. So is there a couple? The question we're gonna treat next time. Is there a couple x, y, such that this type of network does just jump between the two? So there is convergence to a stable state or not? Yes. And sometimes the first vector you give, either you can give it on the one side or on the other, is the same because it's bidirectional. It's called a key. So you give this key and then the thing starts running. And you're asking yourself, does this thing converge to a stable state? We're gonna see this next time. I hope everything is fine. Do you have questions about anything? Next time is gonna be fun because all field network is fun.